Okay. Hello, everybody. Good morning. Happy Friday to everybody. I just want to start today with a reminder that the top folder in our My Open Math site is for announcements. And in that folder, we have the integration techniques list that I created, the little PDF. And then I have a bunch of videos on brushing up on sequences and series, because in about 2 weeks, maybe 2.5 weeks, we'll be starting into sequences and series, the biggest chapter in all of Calc 2, basically in all of calculus. And so it's a good idea to brush up on that sequences and series before we get there. Other than that, that's all I really wanted to say there. Oh, and I suppose I should say, that we are currently in section 7.4, and I didn't post the video from Wednesday yet. The lecture, our lecture, in-class lecture. I haven't posted that yet because I've been busy. But 7.5, I don't lecture in class because it's just a review of everything we've gone through with integration techniques. So I just have a couple videos, one being a summary of all the techniques and how to tackle all of the styles of techniques we have. And then the second video is just 5 examples, although it is somewhat of a longer video. I think it's 40 minutes. But that's mainly because I'm talking my way through how I do my decisions on which integration technique I'm going to use, that type of thing. So it's not a requirement that you watch that second video. If you feel very comfortable with integration techniques, then the first video is probably good to watch, just to get a holistic view, an overview of how to tackle integrals in general. And then the PDF integration techniques is there as well if you want to just access it from that folder. And the 7.5 homework is actually up. It's due next Friday. The 7.5 homework is there are probably, I think there's 120 different integrals in there, but I have it randomly select only 25 for you or something like that. So it's a 25 problem homework, but it's from about 120 different integrals. And then 7.7's up as well. Yeah, look at that. And 7.7 will mostly do during class time, except for 2 examples, which just are extra examples, so that if you need them, they're there for you. All right. That being said, let me share my laptop screen. There we go. No, 7.8 is the last section in the unit. That's 7.7 is numerical integration, and 7.8 is improper integrals. So it's close to the last section, but it's not the last section. Where we left off last time was working with this integral. Evaluate the following, right? So let me go ahead and zoom in, remind you of everything we had been doing. So partial fraction decomposition. So let's just pretend we're not even in the section partial fraction decomposition, and you're working on an exam, final exam or exam on chapter 7, and you're handed this and you're asked to evaluate. How do you know that partial fraction decomposition is pretty much the only way you're going to do this? It's because it's a ratio of polynomials. Now, that's not to say every ratio of polynomials can be is best done using partial fraction decomposition. It's that if a simple U substitution can't be used, then it's likely going to be partial fraction decomposition. So in this case, a simple U substitution is not going to help me out with this integral. I can easily see that just because the numerator is an absolute mess. So instead, I immediately just think, well, they gave me a factor denominator, so partial fraction decomposition. And the way we do that, how we decompose that fraction, is every single factor in that denominator, it has an associated power with it. So that power tells us how many fractions are associated with that denominator. So the x minus 1 to the first means I have a single factor or fraction with x minus 1 in its denominator when we split it apart. The x squared plus 4 raised to the second tells me I have 2 fractions dedicated to that factor, one with the first power and one with the second power. Also note, again, this is just a reminder from last time, but also note If it's an irreducible quadratic in the denominator, which both of these are, its numerator will be a linear. Otherwise, if it's a linear factor in the denominator, which is what this guy is, its numerator will be a constant. That's about it. All right, so then from that point, when you set this up, you multiply both sides of what we did is I covered up this stuff. I covered this and this and this, and I said, let's go ahead and multiply both sides of that equation by the LCD, which is x minus 1 times x squared plus 4 squared. So when we multiply both sides by that, oops, get rid of that, we got this blue ink right here. Very top blue ink, that is. And then we did SS, which is strategic substitution. We looked at that right-hand side and we said, okay, so what would turn off some terms? What value of x would? And we let x equal 1, and that ended up turning off all of this stuff right here and allowed us to just say, oh, okay, well, on the left-hand side, if x is equal to 1, we get 50. On the right-hand side, if x is equal to 1, we get 5 squared, or 25, divided by 2. We find out that a, the numerator of x minus 1 in our integral, that a value is going to be 2. Then from that point forward, there was really no other substitutions that would turn off factors. And that's because they're irreducible quadratics. They can't turn into 0 when you plug in numbers. They just won't. So instead, you have to do regular substitutions. This equation at the very top is true no matter what you choose for x. So make some good choices for x. Nothing's going to turn off, so you're going to end up with some arithmetic. But notice what we get in the end. We get these 4 equations. We chose x equals 0, -1, 2, and -2, basically small numbers that are not fractions. And we get these 4 equations right here. 1, 2, 3, and 4 equations. That's 4 equations with 4 unknowns. Now I'm going to go ahead and clean this up. So this is where we left off. That's where we paused last time. So from this point forward, I'm going to clean things up. I'm going to keep the constants on the left-hand side and keep the variable terms on the right-hand side. So for example, that first equation is going to be, I'll subtract 32 from those sides. It's going to be 4 is equal to, I'll leave some space and I'll put a negative, wait, actually I don't need to leave that much space. I'll put a negative 4c and a minus e. You can see that's how that equation simplifies. The next equation, which is this big old mess right here, the one with the 42 on the left-hand side, that's going to take a little bit of extra thought. Let's see. We have 42 on the left-hand side. On the right-hand side, we have twice 25, or in other words, 50. Subtract 50 from both sides, and we'll get a -8. So equation 2, we have a -8. And now let's look at b here. B is going to be -10 times -1, or in other words, a +10. I don't need to put the positive there. I'll put 10. So really, it's just a bunch of arithmetic at this point. There'll be a -10c. There's a +2d and a -2e. Notice I'm kind of aligning things very nicely because either I'm going to use a matrix to solve this, or I could use back substitution if I want to. Let's see, the next one is 90, so equation 3 is 90. Let's see, 64, twice 64 is 128. 90 minus 128 is a -38. There's a lot of room for me to make arithmetic mistakes here, by the way. So let's see, 28, 38. Yes, that's right. And let's see, on B, we have 2 times 8, 16b. On C, we have 8. On D, we have 2. And on E, we have 1. And then let's see this last equation. Okay, 64. So we have another. Oh, it's because of the negative. I was wondering why it's the same 128 right here, but it's because that was the one with the square, I'm assuming. Yeah, x squared plus 4. Okay. So that's 128, and we're losing 62, or I'm sorry, it's negative 128. We're gaining 62, 128, 120, 60, 66, negative 66. The negatives annoying me. So negative 66 equals, and then let's go ahead and fill in the rest. Negative 24 times negative 2 is positive 48. B. A negative 24C. Let's see here. Positive 6D. And a negative 3E. All right. So before tackling this system of equations, this 4x4 system, a couple things you can do to ease the work. One thing I'm going to do, just so that you can track my changes, is I'm going to copy this. And then I'm going to scroll down here. Nope, I guess I'm not going to scroll down there. Undo that. And I'm going to scroll down and I'm going to paste. Now I'm going to put this right here. And the reason why is because I'm going to showcase that before you do any type of matrix solutions, if you're going to use a matrix, you want to make sure that you minimize the nastiness of the equation. So like the second equation, I'm going to divide it by 2. So 1/2 row 2 becomes the new row 2. I'm just going to remove all these numbers here. So this will be a 4. This will be a 5. Right. So this is just basically algebra at this point. But people haven't seen matrices in a while, so it might be nice to see them here. The third equation, there's not much I can do, but the fourth equation, I could divide everything by 3. So 1/3 row 4 will become the new row 4. So let's see, third 22, third 16, third is 8, third is 2, third is 1. All right. And from this point forward, we're pretty much ready to rock. Yeah, just thinking, do I want to use substitution instead? Substitution almost seems to be faster, but I'll use a matrix. Okay, so building this into a matrix, I'm going to shorthand it a little bit here, and I'm going to try to choose wisely, but there's not much you can do to make this really work nicely. So I'll use row 4 as my first row. 16, negative 8, 2, negative 1, augmented with negative 22. And then I'll just copy rows 1, 2, and 3 as written. So 0, negative 4, 0, negative 1, 4, and let's see, 5, negative 5. 5 and negative 5 are going to be kind of a pain, I bet you. Negative 4, and then 16, 8, 2, 1, and negative 38. All right, so there's our matrix. Now, if you have not seen matrix arithmetic, I cannot possibly in a short lecture describe it to you. You're just going to have to hold on and enjoy the ride, I guess. So here we go. I'm going to go ahead and take a negative times row 1 and add it to row 4 to become the new row 4. So negative row 1, add it to row 4 to become the new row 4. I'm also going to take, gosh, this one's going to be kind of a pain, honestly, but I'm going to take 5. Yeah, 5 times row 1 and subtract off. I think it'd probably be easier to say negative 5 row 1. Negative 5 row 1 and add that to 16 row 2 to become the new, or row 3, sorry, to become the new row 3. That's pretty much probably the best tactic there. So 16, negative 8, 2, negative 1, and negative 22. This skill, by the way, working with matrices is critical if you continue forward in mathematics, because many of you will probably, especially if you're computer science or math majors, are going to have to take linear algebra. And yeah, this happens in linear algebra like all the time. It's the basis for linear algebra. So you will have to work with this stuff a lot. All right, so let's take a look at -5 row 1. I'll just look at it here. Let's look at -5 times that row, and we're going to add it to 16 times this row. So -5 times 16 is -80. Add that to 16 times 5, which is +80, and you will get 0 by design. -5 times -8 is 40, minus or plus 16 times a -5, and that's a negative 80. So -40 minus another 80 is a -120. Not a beautiful number, but oh well. -10 plus 16 is 6. Let's see, 5 minus 16, that's a -11. And then what do we got? 110 minus 48, 62. Let me just double check that, because here's where math can really bite you in the butt. 110 minus, let's say minus 50, that'd be 60. Add back to 62. Yeah, okay. Now we've done that. So row 3 is done. So I'll just erase this stuff up here. And now we're going to take the opposite of row 1 and add it to row 4, become the new row 4. So the opposite of this and add it to that. -16 plus 16 is 0. -8 is +8 plus 8 is 16. -2 plus 2 is 0. Oh, that's kind. And 1, -1, which is 1, plus 1 is 2. And then let's see, -22 is 22, plus a -38. 38 minus 22 is 16, -16. Now, because I have a digital whiteboard, I can kind of speed things up a little bit. However, I'll probably still just copy this and then showcase my mathematics here. So copy and then paste. Let's move that down a little bit. I'm going to divide this bottom row by 2, just because it just makes the math a little bit easier. So I'm going to say 1/2 row 4 becomes a new row 4. I like to do that in between steps, just because it's a lot easier to deal with it. So 8 and a 1 and a -8. All right. There's nothing else I can do with any of the other ones. So at this point, I now focus on, so I've finished working on that main diagonal. I'll go to the next diagonal and use that number to kill everything below it. So let's go ahead and showcase that. Again, I only copied this for that one little move there, which was the division by, oh, come on. I don't know what's going on with my, hello. There we go. All right. Why is this not capturing? There we go. Copy. And let me see if I'm at the bottom of my page. Nope. I'm not. Paste. All right. So let's go ahead and start using this 4 to kill off everything below it. So I'm going to take, let's see, how many times 4? It's 30 times. So I'm going to take 30, I'll take -30 times row 2 and add it to row 3 to become the new row 3. And let's see, I'm going to take twice row 2, add it to row 4 to become the new row 4. You can see it's just a lot of mechanical messiness here. So since I did it, all right, by design, -30 times 0 plus 0 is 0. -30 times -4 is 120, minus 120 is 0. -30 times 0 plus 6 is 6. -30 times a -1 is 30. Minus 11 is 19, which is not beautiful, but it is what it is. Let me make sure that I just did that right. 30 minus 90, yes. And then let's see, -30 times that 4 is -120, and add back 62. So 120, 60, 58. -58 though. Okay. double check my math as I go through this. And then let's see, twice row 2 added to row 4. So twice 0 plus 0 is 0. Twice -4 is -8 plus 8 is 0. Twice 0 plus 0 is 0. And twice -1 is -2 plus 1 is -1. And twice 4 plus -8 is 0. And actually, magically, we're already in triangular form is what we'd call this, where the main diagonal is non-zero and everything below it is 0. So that's called triangular form. You could back solve at this point. One thing I will do, though, is I'll divide this bottom row by -1 because there's no need to keep that 1 there. I personally like Gauss-Jordan elimination, which is the full elimination process. So if you don't mind, it's a good review for you anyway. I'm going to continue with this, and I'm going to go ahead and completely solve out this matrix. Like I said, it's a good review anyway. So just to review, once you have used these main diagonals to kill everything below, this main diagonal to kill everything below, and this main diagonal to kill everything below, then you start where you ended and use that to kill everything above. So there we go. How do I use a 1 to kill off a 19? It's pretty easy to do, actually. You just take -19 row 4 added to row 3 to become the new row 3. You take positive row 4 add it to row 2 to become the new row 2. You take positive row 4 add it to row 1 to become the new row 1. This happens very quickly, so just watch how it goes. -19 times 0 times 0 times 0 plus anything above doesn't change the stuff above. So really, when you do this entire process, the only thing that's going to change is this row right here. Anything that was associated with a non-zero value in row 4. So essentially, the only thing that's going to change is row 4. So -19 times 1 plus 19 is 0. 1 plus a -1 is 0. 1 plus a -1 is 0. It happens very quickly. There's nothing else that will change because the rest of the values in row 4 were zeros. You add 0 to anything and it remains static. So nothing we need to do there. Now we move on to row 3. Now row 3 has an oddity with it in that I'm going to go ahead and force this to be a 1 now. And that means dividing both sides of that row by 6, which gives me a fraction. And I freaking hate working with fractions. But it is what it is. We're at that point where fractions get introduced into this matrix. So let's just go ahead and do it. I'm going to copy that, paste it. I don't know where it pasted though. So I have to figure out that. Paste it down there. Okay, let me grab that. So I'm just going to go ahead and at this point divide row 3 by 6. So 1, 6, row 3 becomes the new row 3. So this will be a 1. And then 58 divided by 6 is what, 29 thirds? Yeah. So that's just pretty ugly, and that's how life is at times. And now we're going to go ahead and use row 3, that 1 in row 3 to kill off that 2 in row 1. And for some reason, this is just not liking me today. So copy. Okay. And then I'll go up to, actually, I could probably do this at the bottom of the page. Paste. Yeah. Still got a little bit of room there. So we're going to take negative twice row 3, add it to row 1 to become the new row 1. So let's see. Remember, anything with zeros, those aren't going to change the values in row 1. But anything without zeros will. So -2 times 1 plus 2, that will zero out that 2. -2 times that -29 thirds is a positive 58 over 3. I'm going to have to write that down so I keep it in my brain. And we're going to add that to a -22. But remember, -22 is a -66 over 3. So we have 58 over 3 plus a -66 over 3. It's a -8 thirds. Now I can erase that. I'm also simultaneously here, since I can, I'm going to divide row 2 by -4. So -1/4 row 2 becomes a new row 2. It's just really fast to do that. And by the way, when you do this in practice, it's much faster than what I'm doing. I'm just talking my way through it. Normally, I would be going very quickly if I wasn't saying anything. I'd just run through this. So just to let you know, working with matrices can be very, very fast once you're used to it, but it does take a while to get used to it. I used to really enjoy them when I was a student. So let me go ahead and go just up to, maybe I'll just go up to right about here, paste it. All right, there we go. Remember, this is just to split apart the integral. We haven't even started integrating yet. All right, so let's go ahead and take 8 times row 2, add it to row 1 to become the new row 1. 8 times this 1 added to a -8, that becomes 0. Now we're in complete form here. And 8 times a -1 is a -8. Add that to a -8/3. So -8, which is a -24/3. Add that to a -8/3, it's a -32/3. And now finally, now I can just do this in this step, divide both sides by 16 on that first row. So dividing this by 16, I get 1. Dividing this by 16, I get a 2 here. And there you go. Those are our coefficients. Remember, this is the B column, the C column, the D column, the E column. So we know that B is a -2/3. C is a -1. D is a -29/3, as long as my arithmetic is okay. And E is 0. That's awesome, actually. So let's go ahead and plug those in. Lots of work, right? Just to get down to start an integral. Plug those into our integral. Just to remind you where they came from, right? So let's see. Integral. A was 2. So we have 2 over x minus 1. Plus bx, well, b we know is a -2/3, so I'm going to go ahead and plug in a -2/3 for that b. -2/3 x plus c, and c was, let me just scroll down here, -1. All over x squared plus 4. And then we have dx plus e, d being -29/3 and e being 0. So -29/3 plus a -29/3x all over plus 0, all over the quantity x squared plus 4 and quantity squared dx. There's the partial fraction decomposition for our original integral. Parts of this I can actually integrate pretty quickly. Other parts, not so much. So let's go ahead and break this apart and integrate simultaneously. So that first term will obviously integrate to 2 natural log absolute value of x minus 1. That's done. The next term I'm going to split, because if you keep those two things together, it gets a little bit messy. So I'm going to call this -2/3 integral of x over x squared plus 4 dx, and a negative integral of 1 over x squared plus 4 dx. And you should be able to see that one of those, specifically this guy right here, is a tan inverse. So keep your eye out for that when you do these. The next term in line, I'm going to factor the -29/3 out. And I have the integral of x over the quantity x squared plus 4 and quantity squared dx. Looking through each of these, you can tell that when you do partial fraction decomposition, and you're kind of forced to, it's partial fraction decomposition is not a method that you say, well, I have these choices of 5 different methods, I think I'll do partial fraction decomposition. No, that's not how it works. You use partial fraction decomposition if you have to. And in this case, we just had to. So that's how it is. But when you get there, you'll have a lot of integration techniques you have to use and a lot of algebra. Luckily, most of the results from a partial fraction decomposition are just u substitution stuff. So like this guy right here, I'm going to let u equal x squared plus 4 so that du will steal away a 2x dx. I happen to actually have exactly a 2x dx to steal away. So those highlighted items right there will be stolen away for a du. There we go. Cleans up super nice, right? The next one is actually an arctangent. Again, I gave you a theorem last class. However, it's so soon that you probably haven't committed that theorem to memory. And to be honest with you, I don't. I've never committed that theorem to memory. Instead, I just rederive it every time I need it, which is sort of a stupid thing for me to do, but oh well. So here's what I do. I'm going to look at that denominator. I'm noticing that this right here looks like a tan inverse, but that should be a 1. So I will factor a 1/4 out of the integral. If I do that, that plus 4 is now a plus 1. And temporarily just writing this in here so you can see it, that x squared would be an x squared over 4. However, I'm going to write it as an x over 2 squared. Now it's just 1 over picture squared plus 1, and I know that's going to be a tan inverse of the picture with an adjustment because that picture is being divided by 2. So we'll take care of that in a moment. The final integral is the same type of substitution we did earlier. This time I'll let v, so because u is being used, equal x squared plus 4, so that dv will steal away a 2x dx. Unfortunately, I don't have a 2 to steal away, but so I'll move that over. So the x dx gets traded out for a 1/2 dv. I'll move the 1/2 out front. So negative 29 over 6. And then we have the integral of dv over v squared. Now running all the integrals. 2 natural log absolute value of x minus 1 minus 1/3 natural log absolute value of u. And if you don't mind, I'm just going to resubstitute in right now for what u is. It's x squared plus 4. You technically don't need absolute values on that, by the way, because it's an x squared plus 4. So you could, in this case specifically, just use parentheses. Or not, you put absolute values. You're not wrong if you do. And then minus 1/4. We know the antiderivative of 1 over object squared plus 1, as long as that object is a linear object. The integral of 1 over object squared plus 1 is the tangent inverse of that object. However, you see that linear object right there is being divided by 2. So you need to offset that division with the opposite of the division, which is multiplication by 2. That's where that came from. So let me just point my arrow like that. All right. And then the last one is a negative 29 over 6. However, we're integrating. I dislike how that's written, so I'm going to write it this way. Oops. We're integrating v to the negative 2 dv. So when you add 1 to the power, you get v to the negative 1 divided by negative 1. So it's going to actually be positive. It'll look like that. However, we know what v is. It's an x squared plus 4. And then finally, plus c. And that is the antiderivative of that integral, x cubed plus blah, 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 blah. A lot of work for a problem like that, right? It is. Partial fraction decomposition can be fast if you have a small-ish integral, or integrand, but generally speaking, it can be a lot of work. All right. To allay any concerns on an exam, you will not have a huge integrand for your partial fraction decomposition. So don't freak out. You will not have to solve a 5x5 system or something like that. If there are no questions on that, I'll move forward. If there are, just type them in the chat and I will answer them. I did this in a video example, so I get to skip past this. And you can probably tell why I would do something using a video example in this section specifically, because a single example takes a while. So now we finish out all of our integration techniques with one last teensy little itty bitty integration technique. It is a U substitution. Surprise. It is nothing new for you. So this is what's going to be nice about this, other than the fact that it's just a consideration when you're integrating. So let's suppose, again, this is an exam or something like that, and you're being asked to integrate this. A lot of people will do a U substitution here, which is actually a great tactic. Nothing wrong with that. But what people will do is they'll let U equal x minus 3. And that's just not enough. Why don't you let U equal the cubed root of x minus 3? That is what's called a radical substitution. And it's essentially just a U substitution. So I'm going to let U equal the cubed root of x minus 3. Now, if you want to find what du is, because you have to find out what du is, if you want to do that the way this is written, that'd be a bad idea, because then you have, this is x minus 3 to the 1/3 power. And when you take the derivative, you get 1/3 x minus 3 to the negative 2/3 dx. It just looks really ugly. So here is an option you can always exercise. There's no exception to this. You can always do the following. If your U substitution equals a radical, before you find out what du is, get rid of the radical. Cube both sides. I personally dislike fractions, and I dislike taking derivatives of radicals. So look what I have. No radical, no fraction. Now I'm going to go ahead and take the derivative of both sides implicitly. The derivative of the left-hand side is 3u squared, then du. Differential right-hand side is dx. Now I know what dx is being traded out for immediately. I know what the cubed root of x minus 3 is being traded out for, again, immediately. I have this x plus 2 in the numerator. Well, that's not a biggie, because I can add 5 to both sides of this second equation. And if I do that, I get u cubed plus 5 is equal to x plus 2. You might have been wondering, why is he adding 5? It's so I can get x plus 2. So I know what x plus 2 is. So all those pictures I will trade out. But remember, when you do a U substitution like this and you have a definite integral with limits, be certain to change those limits as well. So luckily, these limits are kind of easy to work with. If x is equal to 4, well, u is equal to the cube root of 4 minus 3, or 1. If x is equal to 11, u is equal to the cube root of 11 minus 3, cube root of 8, which is 2. Now there's no reason for me to ever go back into the world of x. I'm completely immersed into the world of u, and I do not need to step back. So I'm just trading in all the stuff. X plus 2 is u cubed plus 5. This cube root of x minus 3 is u, and then dx is 3u squared du. I'll move this, by the way, that's a multiplication there. I'll cancel this u into 1 power of the u there. I'll move the 3 out front, and I'll distribute the u through the rest of them. So it's a u of 4th plus 5u du, and there we go. This is super nice compared to the previous example. It's kind of what you hope for, right? From 1 to 2. Let me just double check that I did everything there. Yep. Yep. Okay. And now evaluate. It's 3 times the quantity 32 fifths plus 420, 410, 10. Yeah. And then minus 1/5 and minus 5 halves. I'll leave it like that because I want to. Okay. So there we go. That is again, a kind of an oddball topic, right? Because we're in the middle of partial fraction decomposition and all of a sudden we're doing U substitutions. That seems kind of weird. The reason why I think I can't really claim that I know exactly what the author's thinking, but I think the reason why the author of this text does radical substitutions this late within integration techniques is because it often does actually lead to partial fraction decomposition. So when you do a radical substitution, be aware you can actually get a partial fraction decomposition from it. So heads up. If you have any questions on what I've done so far, please ask. I'm going to mute myself while I take a drink. Otherwise, I'll assume that you're dreaming of your weekend. All right. Moving forward, evaluate. Again, another perfect example. In fact, this great exam style example, this is a wonderful exam style example, in fact. So I say that, but a lot of examples are good exam style examples, but I just personally really like this problem. So if you go through the tactics we've learned, the first tactic you learned really was U substitution. So immediately I know a U substitution is going to work here because I can let U equal that entire square root. This guy right here. So that's going to be my top tactic. Honestly, if I go through a list of tactics and one of the opportunities includes a U substitution, that's probably what I'm going to do. But I might as well talk about the rest of the ones, right? So we have U substitutions, and then we have by parts. This is not a product of functions. It's not an oddball function, so it's not a by parts. It's not a product of trig functions, so I'm going to not worry about that. And let's see, not a product trig. Oh, it's definitely not a trig substitution because it's not a difference of squares or something like that. And then it's not a partial fraction decomposition that I can see. So the only thing that I really know to do here is a U substitution. We're going to let U equal that square root of x plus 10. You could actually let it equal 3 times the square root of x plus 10 if you wanted to. I'm not going to, but you could. Then, because I dislike radicals, I will square both sides. And now I will find out what du is. Taking the derivative of the left-hand side, you get 2u and then the differential du. Taking the derivative of the right-hand side, you get just the differential itself, dx. So I happen to know what dx is. I also happen to know what the square root of x plus 10 is. I also happen to know what x is when I go ahead and solve this guy for x. So I'll highlight that. And the 2 upstairs is just a 2 upstairs. Yay! So this is, because it's an indefinite integral, we can't leave our answer in terms of u's. We'll have to trade back into the world of x's at the very end. But let's go ahead and do all these substitutions right now. I'll at least pull a 2 out. That's just an annoyance. dx is going to also have a 2, so I'll just park that out front. U du. Downstairs, the x is going to be a u squared minus 10. Minus 3 times the square root of junk, which is u. And looky, what we have. This is going to be 4 integral u du all over u squared minus 3u minus 10. That could be done using a substitution if you want to. It'll involve a little bit of work, but no matter what you do, because you have that quadratic downstairs, you're going to have to end up eventually using partial fraction decomposition. There's just no way around it. You could try it without partial fraction, but I'm going to tell you, you're going to need a partial fraction decomposition in the end. So I am just going to set it up right now for partial fraction decomposition. And here we go. Let's start diving into this. Now, remember, what's nice about this guy is that it's going to be a super fast partial fraction decomposition. Again, a really good exam problem because it showcases that you know how to do a radical substitution. It also showcases to me that you know how to do partial fraction decomposition. So let's see. Pretend as though this fraction was equal to this fraction, and you multiply both sides by the LCD. If you do that, you get, actually, I'll do it. Yeah, I can actually fit it over here. I'll do it over here. If you did that, you'd get u is equal to, oh, I'm sorry. I should probably do one little step in between. Equals 4. I totally forgot that. I should probably preview what this looks like. Times the integral of some constant over u minus 5 plus a different constant, there we go, over u plus 2. Now, pretend as though these two are equal. That's what I really meant to say. And multiply both sides by the LCD. There we go. If I confused you earlier, I'm sorry. If you multiply both sides by the LCD, you'd get u is equal to a times u plus 2 plus b times u minus 5. And this is beautiful because all you need to do are a couple strategic subs. It was supposed to be a T, but strategic subs. So the first strategic sub is u equals -2. That will turn off the a term. If you do that, the left-hand side is -2. The right-hand side is b times a -7. So therefore, b must equal 2/7. And the other strategic sub is u equals +5, because that would turn off that term. And when you do that, the left-hand side is 5. The right-hand side is a times 7. That is a is equal to 5/7. Very fast by parts, or not by parts, but partial fraction decomposition, which I will from this point forward call PFD because it's just faster. So this integral can now be rewritten as the integral of 5/7 over u minus 5 plus the, 2/7 over u plus 2 du. And now we anti-differentiate. So 5/7 times 4 is going to be 20/7. Natural log absolute value of u minus 5 plus 2/7 times 4 is 8/7. Natural log absolute value of u plus 2 plus c. And now we go ahead and substitute back in what u was, which is the square root of x plus 10. It's going to be 20/7. Natural log absolute value, square root of x plus 10 minus 5. Notice how I leave a space there. Algebra mistakes happen. And so people, if they don't leave a big enough space, they start convincing themselves that that square root covers the -5. It doesn't. So just a little habit that I have. Plus 8/7, natural log of square root x plus 10, let's see, plus 2. Okay, notice, by the way, I didn't use absolute values on that natural log on the second one because it's a square root plus something. It's never going to be negative. So I don't have to worry about having absolutes. You could use absolutes on that. You would still be marked correct. So don't worry about that. All right. So that is the antiderivative of that integral. Radical substitutions are pretty entertaining. I think that they're really cool. The u substitution that you use and then squaring both sides makes it a very beautiful derivative, very easy to work with. Again, if you have questions, shout them out. Otherwise, I will go forward. Let me just check something very quickly. Okay, good. All right. last example for this section, because the other page was a video example I did in a video. You can see it looks kind of fun, doesn't it? That's a good one. That's one where I completed the square in the denominator. So anyway, you can see that in the video. So last example for 7-4 before we head into 7-7, because 7-5 is just a review of all our techniques. And there's a video for that. So evaluate this. This, generally speaking, is probably the most confounding type of integral for students. And I have a video with another version of this so that you have practice. But this generally is tough. So how do you do this? If you look through all our techniques that we've learned, U substitution, this is totally viable for a U substitution. In fact, I would start by rewriting this as the integral dx over x to the 3/8 minus x to the 1/4. It's just a little bit easier to see what you're working with. But there are some major issues here. You have to decide what U would turn into, right? So you could say, well, I'll let U equal, let's say, x to the 1/4. The problem with that is that you can't really write x to the 3/8 in terms of U very easily. Also, when you let U equal something like x to the 1/4, let's just pretend, and you raise both sides to the 4th power to get x, and then you say, oh, that's 4 u to the 3rd du is equal to dx. That's great. Awesome. Good for you. So now you know what dx is. Now you know what this is. But again, you're still kind of stuck. What the heck is that guy? It's a bit of a mess. That actually is going to be u to the 3/2 is really what that would turn into. And you're back to square one because you don't have all monomial terms. You have something that is with a rational exponent power. It's not a really good substitution. If you try, so I'm going to cross it out. If you try u equals x to the 3/8, you'll have the same issue. So what do you do in this situation? Here is my advice. Find the common denominator for these rational exponents. I'm going to write this down. So write exponents with common denominator. So we'll start there. So this is equal to the integral dx over x to the 3/8 minus x to the 2/8. Okay. Then factor. If you remember from your college algebra and your pre-calculus courses, when you factor an expression like this, you factor out the lowest occurring power of what they have in common. They have x in common. The lowest occurring power of x is x to the 2/8. So I'm going to factor out an x raised to the 2/8. I'm left with an x to the 1/8 minus 1. And now I will make my u substitution. And the u substitution that I'm going to use, the author will give a hint on a problem like this. Since we're not doing problems out of the textbook per se, then you probably wouldn't receive a hint if somebody else coded it. So I'm going to tell you the hint that the author gives and me telling you not to follow that hint. So the hint the author would give is he would say, let u equal x to the 1/8. And the reason why is because u squared is right here. So now you don't have any fractional versions of u anywhere. But I'm going to go one step further. I'm going to let u equal x to the 1/8 minus 1. So essentially what I'm saying is, if you let u equal that, this is no longer a fractional exponent. It's actually u squared. which is beautiful. It's a u squared times basically like a u minus 1. And that's great. But I think it's a little bit better to say, you know what? Let's go ahead and let u equal x to the 1/8 minus 1. I just personally think that's a good idea. Do you have to do that? No, actually you don't. You don't have to do it. You could probably do just x to the 1/8. I'm trying to see if there's a ramification of... No, I guess you could. In this specific example, you can use let u equal x to the 1/8 or x to the 1/8 minus 1. I'll just do x to the 1/8. It could go both ways. It actually doesn't matter. In this problem, there are some problems when you probably want to tack on the minus 1, but in this case, actually, it does work out nicely now I'm looking at it. So if you let u equal x to the 1/8, first of all, that would imply that u squared is that x to the 2/8. Beautiful. Also, u to the 8th power is equal to x, and therefore 8u to the 7th du is equal to dx. So I happen to know what dx is going to be stolen out for. That's kind of nice. I happen to know what x to the 2/8 is stolen out for. And I happen to know what x to the 1/8 is stolen out for. Well, let's go ahead and do our substitutions. dx turns into 8u to the 7th du divided by x to the 2/8 is a u squared, and x to the 1/8 is a u. That's pretty nice. Oh yeah, I could easily see that if I did that. Let me see. X to 1/8. Nah, I'd still have the issue from before. All right. So when you see this, you could see that at least you can cancel the u squareds. I'll move the 8 out front. I get u to the 5th over u minus 1 du. In this case, you're going to have to do yet another substitution. Very small substitution, but another substitution nonetheless. Or you could do long division. Your choice. You could use long division here. There's absolutely nothing wrong with that. In fact, let me go ahead and showcase that since this is the last example in this section. Grab this guy. I'm going to move it over to the middle of this page. That way I can break this into two possibilities. Okay. Just for those who like to be entertained by different avenues. So one avenue, the avenue I think most people will do actually, is, excuse me, is they will go ahead and do another sub. So they'll say, let v equal u minus 1, so that dv is equal to du. Looks like you're not really doing much. However, you are, because then you're saying v plus 1 is equal to u. And now when you do that, your integral becomes 8 times the integral of v plus 1 to the 5th over v dv. And all you need to do is multiply out that numerator and divide everything by v, and you're done. To multiply out that numerator, just use Pascal's triangle. There we go. That's the 5th power expansion. So I'm going to write 8 integral of v to the 5th plus 5v to the 4th plus 10v to the 3rd plus 10v to the 2nd. Oops. That's supposed to be a second. It just doesn't look like it. Plus 5v plus 1. All over v dv. Pascal's triangle is super powerful, super fast. So that's really nice. And then obviously you could just break this up. This is 8v to the 4th plus 5v cubed plus 10v squared plus 10v plus 5 plus 1 over v dv, and integrate. 8, let's see, 1/5 v to the 5th plus 5/4 v to the 4th plus 10/3 v to the 3rd plus 5v squared plus 5v plus the natural log absolute value of v. And you know what v is? It's u minus 1. I'm not going to write that. And you know what u is? U is x to the 1/8. So it's x to the 1/8 minus 1 is what v is. I'll just write x to the 1/8 minus 1. So I'm too lazy to write it all out. That's what all those v's turn into. Okay. Now, there we go. Now that's one way you could have done that. The other way is via long division. In this case, I'm going to say via synthetic division, because I think that's a good review of synthetic division. So, synthetic division. I am an adherent to making you use synthetic division. So if you don't know synthetic division, then go learn it. It's awesome. But if you have a polynomial and you divide it by u minus 1, you're doing synthetic division by 1. So here's synthetic division by 1. Our polynomial is 1 u to the 5th, 0 u to the 4th, 0 u to the 3rd, 0 u to the 2nd, 0 u, and a 0 constant. It's actually kind of nice. Bring down the 1. 1 times 1 is 1. Add 0 and 1. 1 times 1 is 1. Add 0 and 1. 1 times 1 is 1. Add 0 and 1. 1 times 1 is 1. Add 0 and 1. 1 times 1 is 1. All right, there we go. So this tells me that that fraction turns into 1 u to the 4th plus 1 u to the 3rd plus 1 u to the 2nd plus 1 u, that's it, and plus 1 over, oh, sorry, that plus 1 is over u because that's the remainder. Let's see, is that right? For some reason, these are slightly off, and I'm not 100% sure why. Fourth, and it's over u minus 1. Sorry, it's over u minus 1. Okay. Let's see. 4, 3, 2, 1. Oh, 0, 1. I do need a 1. 1 over u minus 1. There we go. All right. du. And when you integrate this, you get 8 1/5 u to the 5th plus 1/4 u to the 4th plus 1/3 u to the 3rd, and so on and so forth. And plus c. And this is 8. Now, this is sort of different than what we had. U is equal to, by the way, in this case, x to the 1/8. So, x, oh, sorry, x to, is it 1/8 or 1? Yeah, it's 1/8. We have x to the 1/8 to the 5th, which is x to 5/8, plus 1/4 x to the 4/8, plus 1/3 x to 3/8, plus 1/2 x to 2/8. That was 1/4. Sorry about that. Plus x to the 1/8, natural log, absolute value of x to the 1/8 minus 1 plus c. And if you say, wait, that looks completely different than what you had before, it is. It's because here, I know it's not 1/5 x to the 5/8 here. It's because this has got a minus 1 in it. It's got a different constant in it. So if you were to multiply everything out and clean things up, these would be the same expressions. They just don't look like it right now, but they are the same expressions. So anyhow, synthetic division, I think, is very beautiful. It's also very clean. So I highly recommend it if you can do it. Personally, I think it's a good way to tackle this. Checking something very quickly. 0. Yeah. Yep. Same problem. All right. Yep. Double checking. That's all. So questions, partial fraction decomposition, trig subs, trig products, biparts, U subs, questions on anything, radical substitutions, anything that we've been going through thus far.